In this video, we're going to look at how we can use derivatives to help us approximate values on functions. You'll see what that means in a few minutes. Before we get started, let's talk about equations of lines. This is something we're very familiar with. So say I had you find an equation of this line. Most of you are probably going to look for something like this: y equals mx plus b. What's the equation of the line? So just looking here, we know the y-intercept looks like it's a value of 3, assuming this is a 1 by 1 grid. Each grid value is 1. So the y-intercept is b, and the slope, or the m value, we would say it looks like it goes down by 4, so negative 4 and 5. So our rise or run is going to be negative 4 over 5. So we would say y equals negative 4 over 5 x plus 3. Right? And that's a pretty typical grade 9 math problem. Now, that's one way to find the equation of a line, but there is another way. And this is a way that's going to become very useful. This way here, by the way, is called, we call this slope y-intercept form. Slope y-intercept form of a line, because obviously it has a slope and has the y-intercept in it. So this is useful when we have the slope of a line and we have the y-intercept. But just sort of skipping down here to this question right here. If I asked you in this question, for example, to find the equation of the tangent line at 4, right, for this line, I would be asking for basically a line that looks something like that. The equation of a line is something like that. And it's a bit of a pain to find what that y-intercept is. Just the way I sketched it, looks like it's going to be around 1. But we don't know if it's exactly going to be 1, what it's going to be. So it's not always handy to find the y-intercept. Sometimes it's actually a lot of work to find the y-intercept. So it would be useful if we had another way to express a line that we didn't have to use the y-intercept for. And we do. There actually is another one. And it's based on this definition of slope. We know slope often as y2 minus y1 over x2 minus x1, right? It's just the difference in the y values over the difference in the x values. Now, let's say in a question we were easily able to find the slope, or we were given the slope and we were given a point on that line, right? So let's say we knew the slope of this line was negative 4/5 already, right? So I'm going to plug that in for our m value. And then let's say we were given a point on the line, and it's very clear the point on the line right here, for example. I could choose either, but I'm going to choose this one because it's not the y-intercept. Pretend we weren't given the y-intercept in this case. So this point is 5, negative 1, right? And this would be considered, we're going to call this our x1, y1, right? That's our first point. That's the coordinates of our first point. Let's say we wanted to find the general equation of a line. So essentially what we're going to do is we're going to define another point, which is just going to be not any specific point on the line. So we can just call that point xy. It's going to be a point on the line, and the coordinates of that are just going to be xy. And according to our equation up there, this will be our x2 value and our y2 value. So if we plug all of this into our slope equation, everything we know essentially, our y2 is just going to be y. We just called it y because it's a general point. Our y1 we called negative 1, so that we can just say that that's y plus 1, over, and then our x2 value was just x. We called it the general point x, and our x1 value was 5, so minus 5. And really what we've done here, if you look at what we've done, is we've come up with another equation of the line. It's not explicit in terms of y, right? But this technically is another equation of a line because it has a y in it, it's got an x in it, so any value of x we plug in there, we should really be getting out a y value. Or any y value we plug in there, we should be getting out an x value. It should work the same way as this equation. Now, that's sort of ugly because we've got the fraction there. So usually what we do when we see this kind of form is we sort of cross multiply that x minus 5 up to the top, and you end up getting something that looks like this. Y plus 1 equals negative 4/5 x minus 5. And this is just another form of a line. Sometimes you see people will move the 1 to the other side or whatever, but essentially the general form of this type of line, this type of equation, is like this. It's y minus y1 equals m x minus x1. So this is just another general equation of a line, just like y equals mx plus b is. And we call this the slope point form of a line. The reason why it's called slope point form is because we can easily create it if we're given the slope of the line and we're given a point on the line. The point on the line, by the way, so the point on the line is the x1, y1. So the point, oops, let me write that out. The point on the line is x1, y1. So you don't actually need to know what the y-intercept is to write the equation of a line in this form. That's why it's so useful. So in this next example, you'll see why this is such a useful form of the equation of a line when we're doing calculus. It's actually a lot more useful than the slope y-intercept form because we don't usually work with the y-intercept very much. So example 2 says find the equation of a tangent line of f of x equals the square root of x at x equals 4. So we're essentially looking for the tangent line. I already sketched it when we were talking about that first question. The tangent line will look something like that. Okay, I didn't use a ruler there. You can probably do a better job on your page, but it's going to look something like that, right? So we know the y-intercept is probably going to be around 1. The slope is going to be, it looks like that's approximately 1/4, right? Something like that, just based on our quick sketch. So how do we find this equation? If you're using the y equals mx plus b way, you know you need to find two things, right? You need to find the slope and you need to find the y-intercept. Let's think about it in terms of our slope point form though, right? If we know the equation of a line can also be defined as y minus y1 equals m x minus x1, what do we need to find the equation of a line? Well, all we need is a point and the slope, right? So we can find the point on the line. So this is the point 4 is the x coordinate. And then what's the y coordinate of that? Well, clearly we can just plug in f at 4 equals the square root of 4, which is just 2, obviously. So this point is 4, 2, right? So there we got our point. We got our x1 and our y1, which we can just plug into that equation. And what's our slope of our line? Well, in calculus, we have another way of thinking about slope. Instead of just calling it m, we could call the slope f prime of x. And that's just our m value, right? So in the case of this question, what we can actually do is we can write the slope as the derivative of f of x. And if we do this sort of off to the side, we can see the derivative f prime of x in this case is going to be, well, f of x, let me just rewrite, f of x is x to the 1/2. So the derivative of that's going to be 1/2 x to the negative 1/2. Right? And if we plug in our value of 4, which is the one we're interested in, it's going to be f prime at 4, which is just going to be essentially 1 over the square root, 1 over 2 times the square root of 4, which is 1 over 4. Right? If we simplify that. So now that we have these things, we can plug it into our form here, right? So we're going to get y minus y1, so y minus y1 was 2, equals m, which is 1/4, x minus x1, and x1 was 4. There's our equation of our line. Now, you actually can simplify this a little bit more. We often like to think of it explicitly in terms of y, so you could actually move that -2 to the other side. So it's going to look like this, y equals 1/4 x minus 4 plus 2. And that's an explicit form of the equation line. Notice how we didn't actually need to find the y-intercept here, we just needed to find the one point on the line and the slope, and then we're done. You could easily convert this to slope y-intercept form just by distributing, expanding, and simplifying everything, but I think this way is quicker. Now, if you take a bit of a step back and look at what we've found here, we found the equation of the tangent line to a function. Can we come up with a general equation for a tangent line of a function based on this? Well, let's call the point where we want to find the tangent line C. So let's call this point C. Okay, and we'll call our function, our original function, f of x, as we already know. So what we're going to call this point is going to be c and f at c, right? Our y coordinate's going to be f at c. So we're looking at a general case here now. If we're looking at a general case, essentially the equation of the tangent line, if we think about what we sort of did here and what our slope point form is, our equation of our tangent line is always going to be y equals, well, the slope, right, which in this case is 1/4. So the slope at point C essentially is going to be f prime at C times x minus that C value, right? Whatever that C value was. In our example, it was 4, but whatever that x value is, that's our sort of our x1 value, right? And then at the end, we're just going to add to that our y value, right? This was our y value, so that's going to be f at c. So this, and we can write it in this way, sometimes you see it written as y equals f at c plus f prime c times x minus c, where c is the place you're trying to find the tangent line. But this right here is sort of a quick way to find the tangent line of a function, right, at any point C. So I'm just going to write that here. This is the tangent line of f at x at a point x equals C, right? Some value C. Okay, so that's pretty interesting. We have a quick way now of finding a tangent line of a function. Let's do one more example of that. So I encourage you, example 3 on the next page. Pause the video here, give it a try yourself. See if you can come up with the equation using that new formula for it. Pause it here, unpause when you're ready. Okay, so here we go. I just use this definition of a tangent line to come up with this equation at the end. Of course, we can expand and simplify, but essentially that's it. And the way I did that was I needed to find what the function was at -1, right? Because that's our f at c. And then I needed to find the derivative at -1 as well, which was -1/4. So I found the derivative first and then plugged in -1. And then you just plug in your c value, and this is what you get. We could, of course, simplify. I'm just going to do that last step. If we want to write it in y equals mx plus v form, or expanded form, we can call it. Once you expand out everything there, you're going to end up getting y equals 1/4 or -1/4 x minus 3/4. So that's going to be your tangent line, and that's in slope point intercept form now. The slope point form helped us to come up with that rather quickly without having to find that y-intercept at all. Now you might be wondering why we're doing this here, why we're just doing equations of lines and equation of tangents. This is something you already know how to do. But there's actually a very good application for this. So let me pull up a Desmos window and I'll explain why. Okay, so what I've done here, let me just zoom in there. I've graphed that 1 over x minus 1 that we just worked with, and I graphed that tangent line too. So right away we can see that it looks like we're right about our tangent line. Our tangent line seems to just touch that function at -1, and all is good. So there you go. So we can see that it touches just at that point, -1 and -0.5 or -0.5. So the reason why this is useful, why coming up with these tangent lines is useful, we can see it when we zoom in. So I'm going to zoom in on this function a few times at -1, because -1 is the point in question. So what do you notice as I zoom in here to -1? Zooming into -1. Yeah, you can see that the -1 is here, right? So at -1, what do you notice about the blue tangent line and the red function? What do you notice about them? Well, you'll notice they're right on top of each other, right? If I take away the blue, you can see the red line. If I add the blue is the tangent line. You can see it. They're right on top of each other. So what does this mean? Why is this useful? Well, all it's telling us is that very close to that point 1, or -1 I should say, the tangent line and the function are very close together. They're essentially the same thing, right? As long as we're close enough to that -1 value. The tangent line and the function look the same, as long as we zoom in far enough. If we zoom out, clearly it doesn't work as much anymore. See, when I zoom out to this level, you can see there's a little bit of difference between the tangent line and the function. But the point is, we can use this to approximate values. So say I wanted to find out the value of the function at -0.96. I could plug in 0.96 into our function, but I could also plug in -0.96 into our tangent line function, right? The equation of the tangent line. And the values would be so close together that it wouldn't really matter, right? As long as we're close enough to that point. So essentially what we're doing here is we're using the tangent line. Oops, let me see if I can zoom back out here. We're using the tangent line to approximate, oh, that point's going to go with me. That's okay. We're using the tangent line to approximate the value of the function, as long as we're close to that -1. So this is called a tangent line approximation, and it's helpful to be able to approximate the value of functions around a value. So here's another example. This is an example of how this is actually practical. So say I wanted to approximate the value of square root 4.25. We could just take a calculator, plug in square root of 4.25, but I don't actually have a calculator around me right now, so I couldn't figure that out if I wanted to. How can we approximate that value using this? Well, we don't know the square root of 4.25, but we know the square root of 4 is just equal to 2, right? This is a value that's pretty close to 4.25. So can we use this to determine our value of the square root of 4.25? Well, let's think about it. If we choose the point 2 here, right, on our function, 4,2, so this is the value 4,2. If we had the equation of a tangent line through that point, could we use that to approximate the value of 4.25? 4.25 and question mark, right? We don't know what that value is. Well, if you look at this graph, even this really crude graph right here, you can see that the tangent line and the value of the function, the red line, are very close together. So we could actually use that to approximate that value at 4.25. We know how to come up with the equation of a tangent line. We just did that. So let's do that again for this function. And the function in question here, when we're doing the square root of something, is just f of x equals the square root of x, right? So that's the function in question here. That's the one that we're going to use to help us approximate the square root of 4.25. So again, we can go back to our definition of our tangent line, or just this form of the tangent line. It's going to be f at some value c plus f prime at c and x minus our value of c, right? According to our slope point form of a line. And if we think about what each of these things are, we can actually pretty easily find those. So our c value, our x value in question, where we know all the information, is 4, right? So this is what our c value is going to be for this, right? What's f at c? Well, we know f at 4 is just equal to 2, right? That's the point that we know the value of. Then we want to find this new x value. So our x value that we're trying to find is 4.25, right? That's the value with the unknown y coordinate that goes along with it, right? That's what we're trying to find. We can also find the derivative, f prime of c. So f prime of x, well, the derivative of the square root of x is 1/2 x to the -1/2, right? So f prime at 4 is just going to be, what's that going to be? It's the square root of 1, so it's 1/4. Right? So the derivative, we actually did this in the previous page, but that's the derivative there. So we can just plug these things into the equation in order to do this. So y equals f of c is just going to be 2 plus f prime of c is 1/4. And x minus c, So x is our 4.25 value minus our c value of 4. Just the difference between the x value and the x value that we know and the x value we're looking for, right? So if we wanted to simplify this, 2 plus 1/4, I'm just doing this without a calculator too. You can see that it's not going to be too bad. So this is going to be 0.25 or 1/4, right? So we're essentially going to have 1/4 times 1/4, which is a 16th, plus 2, which if we do this, it's going to equal 33 over 16, which equals, if we do that as a decimal, 2.06 approximately. Now, that's our approximation using a tangent line from x equals 4. We're using that to find that point. How accurate is that? So I found my calculator, just found it. So now I can check by taking the square root of 4.25. How close are we to the value? Well, going up here, square root of 4.25, let's do that. 4.25 square root, oops, I think I just did squared instead. 4.25, I know I'm keeping you all in suspense. You can just plug this into your own calculator. This also equals 2.06. It's 2.06155 if I take it to 5 decimal places. And the 33 over 16, if I take that to a few more decimal places, this actually was 2.0625. Should have added a few more decimal places there. But we can see our approximated value using the tangent line and the function itself are very close together, right? 3 decimal places. You need to go to the thousandth decimal place to get a different value. So we're actually very close, and it's because we're close enough, right? This straight line approximation here, this linear approximation here, was good enough to approximate that value. So we can use this to our advantage when we don't want to evaluate the function at a whole bunch of points. We can approximate it with a straight line because it's very easy to plug points into a straight line. So example 5 is another case where we have something that this is useful for. See if you can pause the video here, try it for yourself, unpause it if you get stuck, and I will go through the problem. So what we have here is a function that we're approximating the value of f at 1.9. So just what's the value of the function at 1.9 if we know that f at 2 equals 1 and the derivative of the function at 2 equals 4. So it sometimes helps to sketch something like this out. We have the function at 2 equals 1. So we're going to have a value of 2, 1. That's a point in the graph. And we know the slope at that point is 4. So that means we're going to have a slope that's pretty steep like that, right? Now, if this blue line represents the tangent line, because that's the slope, we don't know what the function could be doing. I'm just going to make something up. Maybe the function could be going like this and like this. I don't know what it looks like, but we do know the slope of the function is represented by that blue line. Now, we want to approximate the function, not at this point 2, 1. We want to approximate it at 1.9, right, which is a little bit to the left. And you'll notice that that point is very close to 2, right? So again, we're actually going to use the slope of that line to determine the value of the function because we don't actually know what the function is doing. So again, if we go back to how we laid out our tangent line was y equals f at c plus f prime at c times x minus c, right? Using our slope point equation. And so think about it. What's our c value? What's our x value? Or a c is always our known value. That's like the point where we're finding the tangent line. So the tangent line is at 2. So c is equal to 2. F at c, well, we're given that in the question. F at 2, let me rewrite that. F at 2 is going to just be 1. And we also know, just based on the question, f prime at 2 is 4. So, oh, and then the x value we're looking for, clearly the x value we're looking for is just that 1.9, because we're looking for the value of f at 1.9. So we can just plug these things directly into this equation to approximate that value. So f at c is just 1 plus f prime at c is 4, and then it's going to be 1.9 minus our c value, which is 2. Do you even really need a calculator for this? Probably not. If this was on an AP exam, it would probably be in the non-calculator portion of the exam. So it's 4 times negative 0.1, which is going to be 1 minus 0.4, which is 0.6. So does this make sense? Does it make sense that the y value is 0.6? Well, based on our very quick sketch, I think it does, right? Because the y coordinate of this point here, the point that we were given, was 1, and we know the slope of the function is positive, so a point just to the left of that is going to be a little bit less than 1. So 0.6 makes sense. So that's the answer. Notice how we didn't actually need to know what the function was to come up with this. All we need to know was the value of the function and the slope of the function at that point. There you go.